does have some subtleties, and this is what we will talk about today. So what we begin with is we have a so-called vector space. About this we mean X is a set, A is a sigma as a part of that set, and mu is a measure on the sigma as a rod. And then we have various set of functions. We have the positive extended real functions. I want to also emphasize the sigma as a rod. And you have seen before, this is a set of functions, I think they're called U oftentimes, that go from X to the extended positive reals, just so that U is measurable. And by this we mean A, comma, extended real for a measurable. So measurable as a function from this sigma as a graph to the sigma as a graph on the extended reals. So these are positive functions. And then we can consider real functions, and there are two versions of it. One where we take the extended reals, and another one where we just take the reals. And let us emphasize both of them. And again, this is a little example. You could include the sigma as a graph if you wish. And so this would be the set of functions of X in the extended reals. And this is so this is the extended reals, and again, U is measurable, and these are extended real functions. And then just the reals, that would be the set of functions from X to get us the reals. Measurable, so these are real functions. So just that you know what kind of systems of functions will be concerned with, and we have to exclude the otherwise that's special to my students. So what we saw in chapter 9 last week, that was if you have a measurable positive extended real function, then you can associate an integral to it. And the integral would be a number between 0 and infinity, infinity included. And it was like a three-step construction where first you take indicator functions, at least you can view it this way. So if you integrate indicator functions simply the measure of that space, this is about the whole idea. And then the next step, and step 1 and step 2, is to say that, okay, what about simple functions? Simple functions are those which are linear, positive linear combinations of indicator functions, and you write it like this. So the integral of this should simply be some j goes from 1 to n, integral over 1 j, oops, we should have a this yj integral 1 j du, and this again using the first step is the same as is expressed in here. So this is the second step that of how to do it, and let me say the last step is then that if you have an arbitrary function, then the integral is the sum of the integral of fj mu, where 0 less than fj less than mu, and fj is simple. Then just put like this. And this involves quite a bit, because what this last step involves is that if you take any positive measurable function, then there exists a sequence of simple function that converges point y to dash 1, and it's an increasing sequence. So there's an increasing sequence of simple functions that converges point y to u. And that was something you saw in chapter number 8. So it's a really somewhat delicate construction. Then there's the Bobby-Levy theorem that says that the integral is continuous with respect to such increasing limits. So therefore, this definition makes good sense. So this is just a brief review of the idea of how to integrate positive functions. And then we say that most of the work sits in the positive case. So when we go from the positive case to the real case, there's still some work to do, but it's not that bad. So as you also saw, so there's quite a bit involved in this step here, and in this step also required some amount of bookkeeping. The trouble is that if you write a simple function, can be written in several ways in this form here. There are standard forms, and even standard forms are a little bit subtle. So there's a certain amount of bookkeeping to check that this is well defined. So this is just to remind you a little bit about what happened. Okay, so what we do today is that we extend this result. So if we have, say, even for the extended reals, what we want to do is, or real, I don't know if we have, then we want to, maybe even put a question mark to associate an integral of that function. And that most likely should be an extended real number. However, there are some problems that we should see that it will not always be well defined. For example, if you take the function sine of x, if you want to integrate that from minus infinity to infinity, you will somehow see that doesn't work. Because if you look at the area under the y-axis, that is plus infinity, the area over the x-axis also plus infinity, then you have a plus infinity minus plus infinity situation. So we have such problems, and this is what we should try to address, and we do it immediately to see which functions really are measurable. So, but then we first say, how can we reduce integrating a real function to a positive function? So one thing we know we can do is that whenever we have a function that goes from x to r bar, measurable enough, then we can find two new functions, u plus and u minus, that go from x to r bar, that satisfy that u is equal to u plus minus u minus, and by the way, also the absolute value of u is the sum of the two functions, and moreover, u plus of x is given by max u of x common 0, and u minus of x is given as max minus u of x common 0. So this is what we really shall be using, and I could just give you one great example. I'm sure you've seen this already. But if we take the function u of x equal x on the real axis, then the graph will look like this. And let me try to take colored chalk just to indicate where let me try green and so the positive u plus will then be this function here, if you can see it. So this would be u plus, and u minus would be this function here. This is u minus. So this is what it looks like. And you can see, it's very easy to see, if you take u plus u minus, then you get absolute value of the function. also you saw before, that is corollary 8.11. That says that if U is measurable, then so that it goes both ways, U plus U minus. U plus U minus are always positive functions, so the idea here is that if U is measurable, then both of these are measurable and vice versa. So this is interesting for us. Because now we can make the definition, let me see where I put it in, take a fresh step forward. We now define the integral. So suppose that a U goes from x to r, is measurable. And that means that U belongs to this function space that we have called M R bar. Then we say the following. We say that U is U integrable. And this is whole by definition if U plus U minus a finite interval. And remember that in our U plus and U minus are positive visible functions, so these integrals are already defined. This is what you saw in chapter 9. So this is defined using techniques from chapter 9. So therefore this definition makes sense. Then we further say that if U is U integrable, then we define the integral to be U plus the U minus integral U minus du. So this is the definition of the integral of an extended real function, provided it is integrable. And it is clear now why we want to make this assumption, because with the assumptions, both of these numbers are positive, finite real numbers. So what we don't want is, we don't want a situation where we have plus infinity minus plus infinity. That's really what we want to exclude, because plus infinity minus infinity minus infinity is not defined. We cannot be extended to that, obviously. So therefore, make this assumption and we find it in this way. I guess that some of you may say that it would be all right if just one of these two was finite. And that is also true. If there's one of them is finite, you could still define the integral. But we choose to require both of them to be finite because it makes the whole theory work more smoothly. And by the way, I should say that then this ends up being a real number. So the integral of a new integral function is a real number. Moreover, we have some positions. This is script L, and we have one here with a U, or sometimes don't even write a U. This would be the set of functions, or we do like this exercise with R. This would be the set of functions from U from x to R, such that the U is U integrable. And we can also put the extended reals, and here I want to emphasize every time, and this would be function from x to the extended reals. And I think that the book here may deviate a little bit from this. So I really want that if you use these extended reals, then we put a warning sign. So this R extended is a warning sign that we're working with the extended reals. And the warning is because of the following. We really want L1 to be a nice space. We want this to be a vector space. So in particular, we want to have two functions here we want to be able to add them. And the idea is the following, that if u and v are functions from x to the extended reals, then u plus v may not be defined. Take, for example, the trivial situation where u is constantly equal to plus infinity and v is constantly equal to negative infinity, minus infinity. So these are extended real functions. Then u plus v does not make sense. So in this case, we'll have that u plus v at x, that should be the same thing as u of x plus v of x, and that should be the same thing as infinity plus minus infinity, and that does not make sense. So in general, you cannot add two extended real functions together. And this problem did not arise when we only looked at positive functions. So in the real case, we have this problem. So what you should think about is that these functions, they can be added. We are going to prove this specifically, whereas these functions may not be able to take the sum of these two functions. Okay. And then we arrive at I should also add a little bit more notation. As our notation, an integral field is like enough child has many names, and so has integral. So what we write here as u in u, we could also emphasize the space x, and we could also, if you like, emphasize the variable. And there are many other ways of writing it. This would be particularly interesting if it is a function of several variables and we only integrate one of them. Then you really have to tell what variable I'm integrating. We're going to see that in 11 such an example. And then if our measure space is our most loved ones, namely the reals with a relative algebra and the net measure, in that case, we write this as sometimes even like this, where the x then is the vector. And this looks very much like what you have seen in high school, a usual integral. And this is done very much on purpose because, as we shall show in chapter 11, the Lebesgue integral and the Riemann integral are the same. So under some conditions, and I will make them, it's a little bit subtle, and I'll make it precise. So if u is the Lebesgue integral, and it is also Riemann integral, then these are the same. And in most cases, it is a very small subtlety. If it is Lebesgue integral, it is almost Riemann integral automatically. But there's a very small subtlety that we can also really talk about. And of course, one of the very nice things about this is that you have seen here a lot of abstract theory. And what we now get back to is that the integral in this most interesting case, or very famous case, simply reduces to what you already know. So now you can calculate integrals. just using all the techniques, antiderivative, stamfunktioner, and so forth. So okay, so I will talk more about that data, but it's interesting already now to make a note of this fact. So even if we are developing a big abstract machinery, as we are, then when it comes down to computations, we get back to what we have known for a long time. Okay. Let me make one small more note before moving on to the first theorem. So, I mean, the way you can see it now is we have defined now the integral to real functions, and we're going to prove it has some reasonable properties. Same as what we did for positive functions. And it takes a little bit of work, not very, very much. There's one note I want to make. Suppose that u is already a positive function, say the real positive function. Then you could ask yourself, when is u L1, say with the extended reals, with respect to this of u, and this happens if and only if, almost by definition, the integral of u in u is finite. So for positive measurable function, the integral is really the same thing as saying there's finite integral. And the reason is, if you have a positive function, what you have to do is to, if you look at what you have to do when there's a function integral, well, is the positive part and negative part both are finite integrals. But if you have a positive function, then what is the positive and negative part of the positive function? So what do you say? What is the positive part of the positive function? That's the function itself. So the reason is that the positive part of the positive function is the function itself, and the negative part of the positive function is zero, yeah. Thank you. So then you can just plug that into the definition and you will right away see that it's true. Okay, so then let me take the theorem and I'm going to use another blackboard space. Let's see if I can fit it in. Okay, so we have u is now a real extended function. Then the following are equivalent. I don't know if you know the notation. So it means that I now list some conditions, and these conditions are logically equivalent. The following are equivalent. And then the first one says that u is an integral. Extended real integral. And the second one says that u plus and u minus are integrable. And actually, already now we can see that this is clear. That 1 and 2 are equivalent is clear because by definition, u is integrable if u plus and u minus have finite integrals. And this is precisely the same as say that they're integral. Okay, so 3 says that the absolute value of u is integrable. And this is very useful. And then the fourth one somehow just tops it off and says that there exists a w positive extended real measurable whose integral is finite and such that absolute value of u is less than w. And even if this somehow seems a little bit silly, then this is actually also quite useful. So in other words, if we can dominate the absolute value of our extended real function by some positive integrable function, then we also find then our function is integrable. So we have these conditions. So let's see why they are true. And this is not particularly hard. But I should nonetheless say while blackboards are moving, that condition 3 and 4, they're really very useful. Even if it's not a deep theorem, then when we're going to prove the next theorem, if we didn't have this, it would be very hard to prove the next theorem. So let us see why this holds. And as I remarked already, to prove that 1 and 2 are equivalent is by definition. By definition plus by definition, I mean by this definition here plus this fact here. Okay, so let's look at the 2 implies 3. And what we here use is that the absolute value of u is u plus u minus. So if 2 holds, then u plus and u minus both have finite intervals. So hence the integral of u, absolute value of u, that is the same thing as integral of u plus the integral of u minus. So here we use 2 things. We use this formula here, but we also use that the integral of positive function is additive. And this was a non-trivial fact proved in the math paper. It's not easy to see this additive, but we have proved it and then we can use it. So it's a non-trivial fact we're using now. Both of these numbers are finite by if 2 holds, and hence the holds is finite. So therefore, so we conclude, hence, u is integrable, extended real, integrable. And so what we use here is that, so now we know that u actual value u is a positive function with finite intervals, and then again we go up and use this fact, positive function with finite interval into this integration. Okay. And then we apply 4. That is easy because we just take our dominating function to be the absolute value itself. So if we know that the absolute value, if the absolute value is integrable, then we can just take w to be the absolute value. Then we have equality here, and then this is finite. So let us then finally show that 4 implies, say, it is not to take implies 2, because 1 and 2 are equivalent. So what I want to show now is that if this statement holds, which is really the most flexible form, then you can conclude that u plus and u minus are finite intervals. And for this, we again use this fact here, and know that these are both positive functions. So we conclude in particular that u plus is less than u plus u minus, which is absolute value of u, and that is less than w. And similarly for u minus. So both u plus and u minus are positive functions which are less equal to w. Hence, the integral of u plus the u, and then you have another result from chapter 10 saying that the integral is so-called monotone. So if u plus is less than w, then the integral of u plus is less than the integral of w. So we have this inequality, and this was assumed to be finite. And this implies that u plus has finite integral and hence is integrable. And similarly for u minus, I will not write it down. So this proves this result, and then we get to a more complicated statement.